Hello and good afternoon and welcome to the QE2 Conference Centre here in London. Thank you for not coming. Honestly, it's really not the same without you. What I can say is it's 2020 and there's a saying which goes, no plan survives its initial implementation. For 2020, it doesn't survive the second implementation or the third, and by the fourth, you'll be in 2021. We will be back in 2021 on the 16th of June at the QE2 Centre, so please put that in your diaries. I would like to thank Lenovo, AMD, NVIDIA and Unreal for supporting us in our ongoing endeavours to look at the next generation of technology for architecture in the construction market. And of course, brought to you by AEC Magazine and all my colleagues who work with me on that. NXTBLD Virtual is a bit of an experiment this year. We're having 6 days of 1-hour talks. Each talk segment has 3 talks in them at 20 minutes each. And then we're going to have a live Q&A afterwards with your posted questions and maybe a few from me. This year's event, we have a broad range of topics: data-driven design, robotic fabrication, 3D printed concrete, digital fabrication, AR and VR, open and collaborative formats, and also, of course, multi-core and the latest in workstation developments. For the finale this year, we have an extended talk with the Autodesk Letters Group, who have made this year particularly interesting for customers to voice their feelings towards the technologies that they're using today. We're going to have a discussion about the kinds of technologies and the changes to digital workflows that they hope will happen in the next 5 to 10 years, and to see what kind of technologies these guys are looking at. So please wash your hands, face, something like that. We look forward to seeing you on the other side.
Hello and welcome to NXTBLD Virtual. Thanks for joining us in our COVID-friendly conference, generously sponsored by a number of technology firms, including Lenovo, AMD, NVIDIA and Unreal, and brought to you by the AEC Magazine team, without whom none of this would be possible.
Our first speaker this afternoon is Molly Claypool. She's Director of Automated Architecture, a design and technology startup based in London and Bristol. She's also co-director of the Design Computation Lab at the Bartlett UCL. And she was 2019 Fellow in Automation in the Southwest Creative Technology Network. Today she's going to be talking about automating architecture and her research into modular construction methodologies, and also how she has democratized the technology so communities can create the homes that they need better and faster.
My name is Molly Claypool, and I'm one of the directors of Automated Architecture, which we shorten to AUAR and pronounce as OUR. OUR is an architecture and technology studio and consultancy based in Bristol and in London. We started the studio in early 2019, although my co-directors and I have taught and worked with each other for over a decade. We are now 9 people with backgrounds in architecture, theory, product design, computer science, and software development, AR and VR, digital manufacturing, social justice, and activism. We are a spin-off of a research laboratory based at the Bartlett School of Architecture at UCL. The research lab, which we founded in 2017, was originally called Design Computation Lab. In September, we rebranded into Automated Architecture Labs as part of a concerted effort to more clearly develop a memorandum of understanding between our work in the studio and the research of the lab. This gives us a rather unique position where we can harness both the benefits of working in academia and in practice, and a lot of agility in how we apply our more experimental or speculative academic research in the real world. We deal with issues of social justice, including the future of work, platforms, localized manufacturing, and circular economies. We do this through work focused mainly on housing and on tool development. A core belief that we hold is in the potential of automation to provide greater access to design and making processes to more people. Now, housing in the UK is the most unaffordable it has ever been. New housing supply is dominated by 10 big companies who are failing to supply either the quantity or quality of homes that people want and need. So our work aims to enable greater democratization of technology and processes of making and architectural production. We believe that automation should not be centralized, but dispersed or diffused into communities. In our work, we wish to empower communities to take back power, to create the homes and spaces that they need, and provide both the social and technological infrastructure for this to be successful and sustainable for the communities that we are working in, creating and collaborating with those communities to create local jobs. One of our primary mechanisms for automating architecture is an approach, and some might call it a disciplinary project, that is referred to as the discrete. The discrete approach is a radical rethinking of the parts that make up buildings. Instead of architectural parts being constrained to types like column, floor slab, beam, or staircase, we think of them being made of parts similar to the zeros and ones in code. Now, this is based on principles of digital materials, a concept drawn from mechanical engineering. Digital materials have been defined by researchers, such as those at the Center for Bits and Atoms at MIT, as assembled from a discrete set of parts, reversibly joined in a discrete set of relative positions and orientations. What this enables us to do is reduce the number of different kinds of parts in a building, but also increase the capacity for spatial diversity, and therefore the ability of a discrete kit of parts to respond and adapt to the needs of local contexts without increasing costs or supply chains. Now, this is part of a framework for production that sits in critique of the notion of modularity. That's a result of the increasingly industrialized production processes of the 21st and 20th century. It's also a critique of the mass customization found in the digital architecture of the 1990s and of the early 2000s. Now, modularity at the scale of an apartment or a room unit, for example, does not enable the kind of universality that a single discrete part allows, in that the same modular unit cannot be used for all structural or spatial configurations. And while the parametric paradigm achieves near infinite variety, it requires costly and lengthy production chains. So the discrete uses the tools of parametric customization and serialized and modular mass production, but localized geometric differentiation. So we reduce building elements down to a highly reduced family of elements that can achieve multiple but finite orientations. Importantly, the discrete enables a scalability that neither paradigm can achieve. Higher or lower resolution is possible using the same combinatorial logic, in this case to construct a column and a floor slab. Now, what we see this doing is enabling an architecture that is entirely digital. Discrete architecture is architecture that is also perfectly made for automation. For example, digital fabrication technologies such as CNC milling work best when the same part or the same kind of part can be repeatedly cut out of sheet material instead of with customized parts, which also enables us to reduce a significant amount of waste. In this case, for our block type A, a discrete housing system, one sheet of plywood equals one discrete building block. Similarly, industrial or modular robots capable of building also really like repetition in assembly. They work best when they do the same or extremely similar tasks over and over and over, rather than having to be entirely customized in terms of their behavior or their tool paths. And we've referred to this in our work as the notion of discrete automation. Now, we're currently not alone in recognizing the capacity for architectural production to work better for automation. Architecture as a discipline, of course, was a relatively early adopter in terms of the design disciplines of digital tools, and there's a really rich history in architecture of taking on new electronic and digital technologies that dates back more than 50 years. Yet construction remains one of the least digitized sectors globally, with a significant automation gap, and it's only slightly more digitized than hunting. Furthermore, as many people watching this will know, construction has a significant labor shortage, and productivity has flatlined since the middle of the 20th century. Now, the automation gap is both the lack of innovative solutions in construction automation around changing social practices and a lack of innovation and creative thinking for supporting existing knowledges or trades within local contexts. And this has created a situation where technological innovation emphasizes the bottom line, and efficiency is favored over people's lived experiences, their knowledge, and their expertise. And what this results in is a huge amount of skepticism towards digital technologies within the communities most affected by increasing automation. And this is in the face of a predicted loss of over 680,000 jobs in the building trades in the UK alone by 2040. So we believe in Our that it's part of our responsibility to work with those people most at risk to find new ways to support existing workers and community members to discover new opportunities for themselves with technology. So we see discrete automation and its consequences on architectural labor as an approach for closing this automation gap. This then helps achieve a better streamlining of production chains, addressing what has been referred to as the assembly problem. And the assembly problem is the inability of existing approaches to automated or digital design strategies to reconcile effectively with existing building practices. Now, in our book, Robotic Building, published almost a year ago, we expanded on this, creating a larger discussion around what we called robotic building, putting it in the context of the age of automation. It also attempted to rethink the hierarchy of authorship. For us, it was an embodiment of our ethos as a practice in a lab, questioning the role of the single author. In the book, we defined robotic building as the utilization of automated technologies to realize architecture. But unlike research on automation that has occurred previously, this did not place robotic building only in the context of digital fabrication or digital design. We began to identify the impact that automation has had and will have for processes of production and architecture in the built environment, while also extending our argument towards new understandings of how relations between architecture and social practices might be transformed entirely by automation. So while the industrial robot arm is one such instantiation of automation and architecture that the book examines, the understanding of automation presented in the book argues for the dissolving of traditional notions of architectural syntax, an argument embodied in the discrete. Chapters follow themes such as craft, print, assembly, many, and diffuse, and include only realized projects led by the top researchers in robotic building internationally. So what we do in the book is recognize that digital architecture, the result of a more conservative and neoliberal approach to technology, has tried to play innocent in its fetishization of technological and formal innovation. But automation is not at all innocent. It immediately forces positions and questions about what increasing automation would mean for society. For example, do we all need universal basic income? Who owns robots? What jobs remain? What kind of housing will we live in? Will we all live in WeWork-like housing? Now, there are deep cultural issues within architectural production that really highlight the incapacity of our current disciplinary practices to adapt to these questions. Yet, when we use the term automation, architects are suddenly able, or really even forced, to think about these issues of labor, platforms, data, bias, discrimination, about jobs being lost in new kinds of rust belts, and about control and ownership. So we need to then rethink practice and how projects are delivered. In this case, our projects are homes. People live in them. When given the opportunity, it is evident that people do want to have some agency in how their homes are designed and made, not just how they live in them. People don't just want to have the choice about paint color and countertops. So we need to rethink the ways in which those in positions of power influence the way that the built environment is designed, produced, and lived in. Today, existing power structures must change if we are to shift to a society that can cope with the social, economic, and ecological changes that we as a culture and society need to deal with. So in what we do is advocate for horizontal, participatory, and equitable social practices in architecture and technology, where individual autonomy and freedom of individuals is supported in a structure of care. And what we have seen is that this leads to more creative, inspired, and empowered people, and I hope more just built environments, homes, and communities. So how do we bring tools of production to people? How do we put them in the hands of people? How do we rebuild trust in such a striated industry? And how do we empower participation in a way that isn't extractive in terms of value or superficial in terms of meaning? How do we leave our I'm the expert or I'm the I'm the one of all of the knowledge idea at the door when we work with communities. And how could decentralizing these tools into local communities really enable this to happen? And how does this augment and enhance local skills and knowledge? How can we radically rethink how these tools enable the best bits of previous paradigms and enable access to larger quantities of homes and quality design without adding significantly more cost? So what we do is we take an engaged scholarship approach, placing the values of the communities we are working with at the heart of our work. Now, engaged scholarship allows for the equalizing of power relations, of democratic practices, of situation-based action, mutual learning, tools and techniques, and alternative views about technology. And in our, we anticipate increasing automation, but we put at the center the lived experiences of communities and understand that they hold expertise, that they hold knowledge, and understanding that we as architects and technologists really need to listen to. Discrete parts in our projects are combined with easily accessible fabrication technologies, such as CNC machines, for off-site manufacturing of parts, as well as an on-site manual system of assembly that uses off-the-shelf tools and doesn't require any specialist training. Now, this aspect's really important because it enables multi-generational building. In one of our most recent builds, we had local residents aged 12 to 76 as part of our building crew, and in another, 16 to 18-year-olds completed 2 weeks of work experience with us. We have also created a web-based design app in-house that allows for real-time collaboration between groups, using simple rules to communicate what is possible or impossible using a discrete system. This was developed through a co-design process with local residents as part of a larger project around the implementation of a value-centered approach for the deployment of discrete housing systems that was funded by Transforming Construction Network Plus, as well as partially by Southwest Creative Technology Network. It also, importantly, requires no specialist software, only a web browser. Now, other co-design tools that we're working with include an augmented reality application that enables real-time instructive assembly for on or off-site locations. And throughout this year, we have been testing the use of both apps with 2 sets of community members who are either local residents of the projects we are working on or work in the trades. And both groups have been people working as crew on our building projects. So the apps are really the first step in an ecosystem of tools that will expand to include platforms for tension networks and robotic control. And what this allows us to do is to incrementally automate workflows and construction processes while preserving the kinds of knowledge and labor within the communities that may use them or be affected by their increasing use. Now, recently we have worked with 2 communities in differing ways by taking the approach that instead of partnering with large industrial partners, we would partner with community groups and government. Both are hugely disadvantaged by the status quo in that there is a huge lack of trust on the one hand and an inability to really take risks on the other. So in the case of Knoll West in Bristol, we partnered with a community-led digital arts organization called Knoll West Media Center, as well as their digital fabrication hub, The Factory. And I'm going to wrap up with some images of this project in a minute. And in Hackney in East London, we have been working directly with the council's regeneration team, as well as a network of partners that include cultural organizations, dance companies, theater makers, participatory artists, local colleges and youth groups, and future leaders programs, both in Hackney and in the bordering council of Waltham Forest. And what we really wish to do in these projects is provide a very different image than this for what housing production could and should look like. So by embedding production in localized settings, we anticipate the development of a coordinated network at a larger scale operating between these communities and other communities. So we set up a factory in both locations, embedded in spaces used for community groups in the case of Bristol, and a brickwork teaching workshop in Hackney at New City College. Now, in both cases, post-tensioned timber building blocks are used as the main building element. These are, as you may imagine, based on principles of digital materials and enable the reversible assembly of a structure. The timber blocks are secured by using steel rods inserted at predefined repeating connection points and are post-tensioned. The repetition of the timber elements alongside the post-tensioning generates structural integrity at almost any scale. The build of the project in Knoll West Bristol, called Block West, captured the very end of a 6-month development process in the local community, where community members joined our crew, were paid a living wage to participate, and went through alongside us a deep investigation via, of course, the pleasure of Zoom due to COVID, a deep investigation really into their homes, their community, and what kinds of spaces and homes they wanted, they needed, and desired. So it became incredibly important for us to show how rethinking frameworks for automation can generate the tangible and the physical. How witnessing this shift from the virtual to the tangible can embody a complete rethinking of who holds power. How it can begin to enable a culture of adaptation and resilience that holds at its core the impact that change has on communities. And what it demonstrated is that when people can identify what they contributed to a design, they can begin to start unpacking the notion of single authorship, the notion of expert, the notion of us versus them. So it also demonstrated that people, when they can identify what they contributed to a design, they can start unpacking the notion of single authorship, the idea of the expert, the us versus them. And it became so important as a way to show us how we can really construct and frame ways of working that gives an ability to reestablish trust and care in communities. So while Block West is a prototype for automated housing using a discrete housing system, it was contributed to by a huge network of individuals living in Knoll West and in Bristol, many of whom have now discovered new potentials for themselves that they didn't know that they had. So in the end, really, what it is a prototype for architectural production using automation that, can be used for building homes, but it is also a prototype for building community, for building creative adaptivity, for contributing a shared and evolving sense of place and placemaking that we hope can be scalable. Thank you very much.
Our next presenter is Elif Erdeen, an architect, designer and researcher at the Architectural Association here in London. Elif joins us to discuss generative design techniques and the integration of algorithmic design methods with large-scale digital fabrication tools.
Hello, my name is Elif Erdeen, and I'm the Director of Emerging Technologies and Design Emtech postgraduate program at the Architectural Association School of Architecture. First of all, I would like to thank the organizers of NXTBLD conference, and particularly Martin Day, for his kind invitation and for bringing this community together. So briefly, what is Emtech? Emtech is a postgraduate program, master's program, and we offer Master of Science and Master of Architecture degrees. And we have had a long ongoing interest in urban systems and organizations, their evolution under changing climatic conditions. And at the same time, we have had an ongoing expertise and interest in material systems and behavior, and how natural systems can be a resource for developing responsive performance in architecture. And these areas, in combination with the newly founded research interest in digital fabrication, and particularly robotic fabrication techniques, are tied to solve design problems in extreme biomes. This is kind of what constitutes our multi-scalar research approach. And through our research, the question that we are trying to answer is, how are we going to build our cities for the future? In today's talk, I will focus on two key aspects of our design research agendas: technology, particularly robotic fabrication, and sustainability through material efficiency, and how these can be explored and researched via collaboration between academia and the industry. So the talk is going to discuss the ever-growing role of architectural production technologies in the built environment, particularly robotic fabrication, and the ongoing research of Emtech focuses on the evolution of traditional fabrication technologies through the employment of digital fabrication and particularly with an emphasis on robotic production paradigms. And the presented case studies are going to expand on the significance of collaboration with the industry. Through our collaboration with Bureau Happold Engineering, one of the pioneering firms in engineering consultancy, and Fibrobeton, experts in GRC shotcrete technology, innovative computational and fabrication workflows have been developed, integrating freeform design, robotic fabrication, as well as fabrication and assembly tolerances. And the prototypes that have been realized that you are going to see shortly through these collaborations serve as proof of concepts into how academia and the practice can work together for sustainable design solutions. So starting with our collaboration between Emtech and Bureau Happold Engineering, our research agenda basically has focused on integrating two fabrication techniques, curved folding and robotic incremental sheet forming, for the generation of lightweight, stiff building elements. And the primary contribution of the research is basically the demonstration of a methodology that integrates the precise computation of curved folded geometries and the employment of finite element analysis as design drivers for the application of incremental sheet forming for the geometrical and material stiffening of sheet material. So just to give a brief introduction, what is curved folding? It's a highly efficient fabrication method for manufacturing of curved surfaces from flat sheet material without stretching, tearing, or cutting. And RASPIF stands for Robotically Aid Single Point Incremental Forming or incremental sheet forming. And incremental sheet forming is basically a traditional sheet forming technique for inducing plastic deformation on sheet material, and we can automate this process through the use of robotics. This is basically an overall view of the computational workflow that we have developed. We in Emtech have basically expertise in developing custom computational workflows, and by partnering with Bureau Happold, who have obviously significant expertise in structural engineering and consultancy, we developed this kind of custom workflow for our research agenda. So here you can see the bottom-up and the top-down approach that we developed for generating this large-scale prototype, and I will be describing this process. So our initial experimentation basically was focused on evaluating the tolerances between digitally generated curved folded elements and physical experiments. As well as establishing the percentage of material that needs to be removed for mountain and valley creases and the fabrication sequences. And this allowed us to basically understand the structural depth that the components could achieve given a specific fabrication size limit. And in our case, this was within the range of 40 to 80 millimeters of structural depth. While simultaneously, we also started to observe the structural performance of these components under self-weight. And we basically generated the curved folded elements following a mathematical model called the mirror plane method. This is a very accurate way of describing curved folded elements. And while we were generating this mathematical modeling method, we realized that the base triangles had to approximate an equilateral triangle. So following that design objective, we came up with several what is called fitness objectives to then revisit the global geometry and to subdivide the global geometry with approximations of equilateral triangles. So we basically ran a multi-objective optimization algorithm for this part of the research for, like I said before, subdividing the global geometry. And this video shows iterations of the simulation before it reaches convergence. This was done in Octopus. So once we had the approximated global geometry defined, then we applied the mathematical modeling of the component geometry on the global geometry itself, and we generated the, let's say, the final global configuration of the curved folded components. At the same time, with Burr-Heppel, we started generating a series of physical and digital experiments to understand the effects of incremental sheet forming, again, starting on a component level under self-weight. So how the density, the distribution, the depth of these dents can affect the structural performance on a component level. And as you can see here, a component on which incremental sheet forming is applied performs significantly better than a component that does not have this property, the one on the left, both under self-weight and under pressure load. So the goal was to make use of this observation and apply it on a global scale. So what we did was to apply incremental sheet forming on areas that are most stressed, and this would basically lead to the strengthening of the final geometry, which can then perform efficiently under self-weight and self-weight plus wind pressure loading. This is basically the toolpath generation diagram for the dents that we generated for the global geometry and the toolpath simulation of creating incremental sheet forming. And this shows the actual physical process of creating plastic deformation via incremental sheet forming, basically. Now, one of the main challenges in this research was the joints, basically, because all of the joints in this prototype has a custom geometry. So the challenge lied in designing the joints that are connecting them. And what that means is obviously we had to incorporate the geometrical complexity of these various 3D components. We had to also make sure that there was structural integrity, meaning that we had to ensure a continuous load path throughout the structure. So obviously the first idea that we thought of applying was 3D printing, but this was going to take a significant amount of time. So what we did to improve the time efficiency of the fabrication process was to design a composite joint system comprising of a 3D printed mold and epoxy resin cast in it. And this is basically showing the final configuration of the global geometry with each of the components and the joints that were modeled. And this is the actual assembly process that took place in the AA premises in London on the outside terrace of the AA. This lasted for several hours. I think it was 6 or 7 hours long. And here you can see the final configuration with the dents, the joints, and everything assembled together. And what we did afterwards to evaluate the process was basically the final 3D model was 3D scanned, and the digital representation of the installation was made and overlaid with the computational model. So this is the 3D scan of the model and the terrace. And this is basically the point cloud that you see is the 3D scan, and this is overlaid with the computational model, and you can see some of the areas where we observed deflection. And this gave us a really good idea about basically how the physical prototype performed and what needed to be improved further. So as I mentioned earlier, joinery system was quite challenging because of the custom geometry of each of the joints. So for further research, we decided to investigate alternative methods to achieve a stiffer component-to-component joinery system. This was one of the main objectives of the second iteration of our research. In the second iteration with Bureau Heppel, basically the design aim was to create a prototype for Bureau Heppel offices in London that could last for a long period of time. And it was going to be situated on top of the skylight that you see. The skylight is above the entrance area. So this was the design ambition. So initially, again, we revisited the component geometry and the connections. And like I said, the aim was to induce basically geometrical complexity by having only one type of joint rather than having a multitude amounts of joints. So we decided to move forward with a single type of box joint, as you can see here on the right. And again, we went back to initial prototyping and testing in the studio. And this time we were basically focused on changing the component size and the geometry, but keeping the joints similar to each other, as opposed to the initial iteration where the joints were varying, but the components were fairly similar. So this is the plan and an initial assembly sequence. In the meantime, Bureau Heppel began to conduct a series of analyses on the design proposal for the skylight. So here we are seeing the component analysis line model showing the shell elements, component model showing the peak stresses, as well as component deformation. And here we are seeing the design proposal in line with the existing beam on the Bureau Heppel terrace and the beams that are placed, existing beams that are placed on the skylight. And some of the analyses showing the prototype under in deflection under self weight, as well as self weight and snow load, and showing lateral deflections caused by wind. And finally, obviously, what was really important was because the prototype would be sitting directly on top of the skylight, we had to understand how the beams on the skylight would be affected. So these are the components, the highlighted ones, showing where they actually touch the skylight beams and their respective analyses. And this was installed back in February, and these are some recent images, so it is still standing. Obviously, the series of analyses that were conducted by Bureau Heppel has been very helpful indeed. And it helped us to refine the design and showing some details. In this case, just to add a last note on this, the dents were added on the components that would receive the most amount of load, basically. So those specific components were stiffened through robotic incremental sheet forming. And the second case study that I want to present is basically the AA Architectural Association Visiting School in Istanbul that I have been directing for the past couple of years, and our collaboration with Fibrobeton, as I mentioned earlier. Fibrobeton is a company that focuses on GRC technology and shotcreting. So this research presents a novel approach for the materially efficient production of doubly curved EPS formwork for in situ concrete construction, and a novel GRC shotcrete technology application. And the research objectives focus on the development of complex formwork generation and concrete application via advanced computational and robotic methods. And of course, while it is viable to produce formwork with complex geometries, a key consideration for us has been the reduction of formwork waste material. So basically, we wanted to create formwork with zero waste material. And this initial phase of the research was guided by the digital and physical principles of robotic hot wire cutting. So a short glimpse of the assembly and fabrication process of the final prototype here. In order to take full advantage of robotic hot wire cutting, the geometries need to be modeled as ruled surfaces, doubly curved ruled surfaces in this case that you see in diagram A. And in the context of this current experimentation, basically the straight lines that you see map the movement of the hot wire attached to the end effector of the robot. And in the selected design proposal, each component is made up of a set of two unique volumes, which are generated by cutting a single EPS block with the hot wire cutter. And both generated pieces are part of the global formal configuration of the assembly, thereby generating no waste material. The algorithm then distributes all of the pieces according to a global configuration system where all the pieces share overlapped surfaces. As we were developing the computational workflow, our partners Fibrobeton were conducting physical tests in order to observe and see how much curvature could be induced within a single EPS block to ensure that the GRC spring process could be run smoothly. And this is the hot wire cutting process in action in studio, showing how each piece was cut and then tagged, and then kind of semi-assembled indoors, and the robotic fabrication setup. The spraying process was basically performed in 3 iterations. Each of these layers of shotcrete had different mixture ratios. In the first and second iterations, the mixture contained fiberglass particles, hence GRC, and the entire structure was sprayed on. A roll press application after each round tightened the surface connection between EPS GRC and subsequently GRC and GRC. And the last iteration contained only a cement mixture without fiberglass for a smoother surface finish. And this was still the curing process, so this is not the entirely cured version. And these are some of the, let's say, final images of this first round of research. And basically, after concluding this phase, our ideas to extend the research further were, first of all, formulated upon the investigation of alternative methods for in situ formwork. So basically employing a material system other than EPS to act as in situ formwork such that thinner, lightweight sections can be achieved. And our second idea was to experiment with alternative computational workflows to enable increased variation and optimization while considering fabrication times and limitations, meaning that we wanted to kind of move towards the employment of multi-objective optimization methodologies to integrate multiple design objectives related to architectural morphology, robotic fabrication constraints, as well as structural stability. So the primary contribution of the second, let's say, phase of research is a demonstration of a multi-objective optimization methodology that incorporates geometrical form finding, material and fabrication constraints, and finite element analysis during the early stages of design. And the design and construction of a doubly curved large-scale prototype made of textile reinforced GRC shotcrete this time with a robotically fabricated in situ reinforcement system serves as a case study for the proposed methodology. As you might be aware, in recent years, evolutionary optimization processes have gained recognition in architecture and related design disciplines. And the application of multi-objective optimization is not only limited to academic research, but it has also been extended to professional practices as well. And our researchers, our PhD researchers in Emtech, basically have developed an evolutionary multi-objective optimization solver engine called WALL-E. And this engine basically allows users to run evolutionary simulations in Grasshopper through utilizing highly detailed analytic tools coupled with various comprehensive selection methods. So I will describe a little bit this computational workflow. So this process obviously starts with the selection of a design idea and the parameterization of a design, and then a random population of design candidates are generated, and these basically start to be optimized in generations according to the fitness objectives that the user provides the algorithm with. And as I said, generations of design candidates are produced in this way, and they are evaluated iteratively. After the analysis of the candidates, a selection is made and finally fabricated. So this was the design idea that we wanted to basically generate in this phase of research, a kind of a seating area, or let's say an urban furniture. And we parameterize the design. So what is called genes that you see at the top are basically used for manipulating the morphology of the geometry. And in our case, we had 3 fitness objectives. So the first one being to minimize the structural displacement of the global geometry through finite element analysis. The second one was, let's say, more functional in the sense that the objective was to evolve the phenotype towards developing flat surfaces to serve as seating areas. And the third fitness objective was basically executed to evolve the phenotypes to use as fewer metal rods as possible for the in situ reinforcement system. So this was more of an cost optimization type of fitness objective. And by running the multi-objective evolutionary simulation, 3,000 phenotypes with 3 fitness values per solution were produced. And of course, here the visual analysis and recognition of the fitness performance of each individual is very important. You can see how each individual is performing in the diamond chart that outlines the fitness objectives. And of course, the analysis of the data associated with each phenotype plays a very significant role in the selection of the candidates. And this is why WALL-E is a very useful engine, because it allows the user to visually analyze all of the design solutions and to make informed decisions. Because as you can see, morphologically, the design candidates might look similar, but in terms of fitness objectives, they are not performing in the same way. So in the end, we basically selected a design solution that was performing best on average level, meaning considering all of the fitness objectives. And finally, we started fabricating the selected design candidate. So this is showing the custom developed robotic road banding setup, including the jig, the security area, the banding area, the actuation area, so on and so forth. And these are the robotically fabricated steel rods that would be placed under the textile mesh. And this is the assembly process before the mesh was applied. And here we see the mesh being applied on the steel rods and the fixing of the mesh. And finally, the application of the GRC via shotcreting. And obviously, in this case, shotcrete was applied both on top of the surface and at the bottom of the surface to make sure that the steel rods and the textile mesh would stay inside. And again, this process was conducted several times. We had, again, 3 layers of shotcrete with different mixtures of fiberglass. And of course, as you can see, one of the limitations here was the resolution of the final prototype. You can observe some jagged areas, basically, and this is one of the further research aims that we are going to address in the future. And this is showing the partially completed prototype, showing the mesh inside the GRC. So this again takes me back to my initial point about how these kinds of research collaborations between academia and practice can give way to address technological as well as sustainability related issues. And through our collaboration with both Bureau Happold and Fibrobeton, we were able to develop custom computational workflows, and we were able to integrate our expertise in different areas related to computational design, structural engineering, material manufacturing. And one last point that I would like to make pertaining to this is that obviously publications are quite important for us. So these research collaborations that we have had with Fibrobeton and Bureau Happold have been widely published in peer-reviewed journals and conferences in order to share obviously our research results with the architectural and scientific community. And I would like to also thank once again to both Fibrobeton and Bureau Happold for their consultancy and their in-kind sponsorship for our research. And finally, please feel free to visit our websites to get more information on our ongoing research. And I would like to thank once again to NXTBLD and Martin Day for their kind invitation to this conference. Thank you.
Our final talk today comes from Fernando Garcia Blanco and Elena Cassini, who will be showing their joint research work on Robotics, exploring human-robot interaction. How will humans and robots interact in our living environment? How will robots and humans construct buildings? What kind of buildings will we construct where humans and robots coexist together? Let's look at the future.
Hello, everybody. Thank you, first of all, Martin, for showing interest in our project, for allowing us to be here today. And thank all of you for being with us today to show our project.
So what we are going to share is our vision for the building of the future. It is important to think about it as a thesis. So it's more like an opportunity to investigate and think, to open a discussion toward a human-robot relationship that will happen in our everyday life. So first of all, The question is, how do we imagine the human-robot relation in the future? Like this. This is a scary and dark environment. Here the machines and humans are not sharing any space. They are two independent worlds. Or like this, an hyper-developed city, where nature is almost not existing. So our duty as architects is to imagine nice and comfortable spaces where to live, creating studied equilibrium between humans, nature, and progress. We want to embrace the future, but conscious about our origins. It looks like an impossible equation, but somebody says that you can build whatever you can imagine. So without boundaries and projected toward this utopia, we have started to question ourselves how we would like this space to be. So Robotic Core is born as a thesis to analyze how robots will build, manage, but also how they will share the everyday life with us. One of the main points was to analyze and imagine how the interaction with them will be, depending on their skill, on their tasks, but also on their characteristics. Another fundamental factor, of course, is the money. The money involved in the process of construction and management of the building. So many industries have already taken advantage of this challenge. And we can make an easy comparison in the graphic shown. This graphic shows the productivity of non-farm industries in North America against the construction ones. We can see that we are not as productive as they are. In the last years, the growth has been possible just because of BIM and prefabrication.
Robots are not playing a role in this, except of, as we say, prefabrication. But our case is fundamentally different. How to do when we don't need to produce the same car 1 million times, but a building? For a car, you always have the same pieces, assembled in the same way, but not in a building. Even when we are working on large scale and we need to simplify the process with many prefabricated elements, our design will drive to the customization of the detail.
So in construction, we work with unique designs in complex environments. So in the image, we can see the OZ bar. That is a project that has been developed by Moss Architecture. Here, the accuracy and the complexity of the layout would not allow, nowadays, the robotic aid in the construction, with the nowadays technologies. So how do we include robots in this creative equation? Let's have a look to some of the ones that are on the market nowadays.
Starting from the manufacturing industry, a sort of first generation, as they were the first typology to conquer the industrial scenario. They can be used in two different ways: automated for repetitive and simple tasks, or human-controlled for more complex and specific ones. In the first case, they are usually away from humans, working in controlled environments, and when I say that, I mean indoor spaces. Robots like this can print, assemble, and can move heavy loads with industrial precision. However, it is important to point out that they will need constant energy supply. Then we have Robots B, second generation. Smaller in size with limited autonomy, the drones. Fully controlled by humans, they are light and can easily reach different points in the space. Very useful to scan everything around. Moving light loads like a pineapple pizza, and recently applied in studies for pollination, like bees. Credit to the National Institute Advance of Industrial Science and Technology in Japan.
Then we arrive to a third type. So they are fairly new in the market, but we start to know them already. They have been created to work side by side with humans, independently from their environment. The Robot C. They start to be more user-friendly. They can move loads, they can provide with telemedicine, they can assemble. They are moving with freedom on the ground, and they have an intermediate autonomy. They are controlled by humans in most of their complex tasks.
And how does robots will know what they have to build? we need to talk the language, the digital language, BIM. The complete digitalization of the construction process means the collection of every single designed element and its relationships with each other and its environment. We have reached already BIM 7D, facility management. We are talking now about BIM 8D, digital twins. We will link into our smart cities. And looking further into the future, we could see BIM 9D, construction by robots. But it's not enough. We are missing an important part of the equation here. To be able, the robots, to develop the tasks.
So we see how today vision machine learning is becoming a reality. A tool already developed by Tesla, which is starting to allow cars with autopilots to drive, to analyze the surrounding in real time, as we can see in these images. So we can find on Wikipedia the correct definition of it. So machine learning is the study of computer algorithms that improve automatically through experience. It is seen as a subset of artificial intelligence. So they collect all of these experiences and upload them into the robots. This is called deep learning, which is collecting data, adding it to a common database, like considering it like a brain that learns exponentially.
Now, imagine those technologies applied in our industry. The capability to work with independence 24/7. Analyzing the surroundings thanks to the imaging recognition. Detecting potential hazards to gain in safety on site and construction precision as never before. Once built, they will be able to check the parameters in real time to achieve environmental sustainability and human comfort. Remember this graphic? This is how we imagine the future based in those technologies. It will be really a turning point in the whole industry.
So as we were saying, the construction process is one of the phases we see changing in the coming years. So let's introduce our project, Robotic Core. That is the reason we are here today. Since the very beginning of the project, the construction was part of the design process. As we wanted to include the robots, we soon realized how the methods of nowadays were not suitable to our case. So we had chosen to focus on the structure and the cladding, as they are the most challenging elements to be built with robotic aid. So our building is like a tree. The inner structure that you can see is the trunk, where the robots are circulating in the inside, reaching the cladding from the top, where the branches are coming out, connecting the external die grid.
It is made by assembling prefabricated pieces that are shaped to allow the robots running into them toward the inner face of the core. They are working like train rails thanks to a constant supply of energy running in the full length. The robots, thanks to that, can move with total autonomy. Building the rods, they are reaching every level. And here is when I arrive to the next phase. The robots will start to print the main structure, the edge beams and the radial ones, with just the minimum quantity of material required. We were inspired by MX3D and its bridge in Amsterdam. If the robotic core is a vertical piece, the length of the beams changes, allowing the sinuous shape. We have in total 9 different types working as cantilevers, allowing the maximum span for an uninterrupted office space free of columns. We have considered the possibility of having not only the assembling process happening on site, choosing the way of prefabrication over the 3D printing on site. This will save time and money with the current technology. We imagine that in 50 years from now, not only the speed of the 3D printing will increase, but also the resistance of the machines working in outdoors. About materials, it is honestly an open conversation to the future 3D printing capabilities and materials under deposition. Anyway, the hypothesis is aluminum.
So we arrived to the top, where the core expands toward the cladding, flourishing outside and joining with the diagrid. We see that from the high road, the robots are going outside through the rails on the facade, building the diagrid that becomes like a sort of network, where machines move, transport, and eventually assemble the panels.
The structure is now done. It's missing the slabs, walls, MEP, we know. Well, following the same logic, the floor plates will be 3D printed, prefabricated on site, along with the rest. If until now the main character has been the robot A, those industrial arm machines, we think in future phases, robots B and C will take part of the process because of the scale and complexity.
So here the question remains, how does this utopic daily routine in between robots and human works? Robotic core, I was mentioning it before, it's an office skyscraper with 8 typological plans. We wanted to achieve 3 goals: a luminous-free plan office space, a wide central court with a glint of nature, and a controlled circulation path to allow the coexistence between humans and machine speed. So we have decided to merge all vertical connection and MAP in a single belt, which we pushed away from the core to allow the office space to be free from any column. And also the inside part, which has a more relaxed court, where all the gatherings and social events would happen. So starting from the inner space, here we can see an image how we think it to be. The core becomes a green pillar, where vertical greenery is growing over the panels. We allow 3,000 square meters of vertical garden and bushes. So we already have seen and analyzed how robots are running inside, and eventually in between this greenery there would be an empty panel to allow the robot head to come outside and to maintain the garden. In the meantime, we have the pollination drones that are flying around, as well as the delivery drones, which are using the opening of the inside space to fly freely. We have also the spots, which are charging on the platform in the orange area, that are waiting to be a date for telemedicine, serving, and even carrying delivery loads. In the core, which is not accessible by humans, we imagine also industrial robots and elevators which are running inside. So from there, we can see here the circulation path. We see in orange where we assume the robots to go, and in blue, the human path. So during working hours, to avoid interferences in between these two worlds. The inner part works as an arrival point for workers from the elevators, and slow working points, and where there are eventually coffee hubs. From there, we can appreciate 2 main openings toward the office, which are organized in 3 main areas. We have internal meeting points, we have the desks, and eventually the management part. There is only 1 area which is accessible from the inside, and the office space as well, which are the hot desk stations for working from homes, and the servers. The proportion of the cards allow an open view, which never looks directly to the top. This is because we want to guarantee a sort of human scale perspective. And this is achievable because every floor is rotating 22.5 degrees. We also have analyzed the microclimate. So the temperature and the exchange and supply of air in the humidity percentage are checked by sensors. And this is a technology that is already happening in the nowadays building, and we're looking forward to see how this will develop. At the moment, what we assume, and you can appreciate in the section, is that a heat would rise. Meanwhile, the fresh air comes from the main core and the bottom openings, creating a natural movement that helps to keep the air fresh in the core. At the very top, we designed a winter garden that grows its roots in the last floor, where tons of earth over it let it grow with a constant maintenance from robot. So in this section, we can really appreciate how the overall system works. The way the inner core is working as the structural and living spine of the building, connecting from the basement up to the roof. Here there is the sinusoid opening which pivots vertically, creating a visual feature which lays in the perspective where humans and robots connect. We arrive at the top. In this image, we can see that the cladding is not always transparent. This is because we are allowing a gradient of solar cells inserted in the panels. As a building like this would require an enormous supplies of energy, we make sure to provide at least 2,600 square meters of solar panels on the cladding. At the end, we come to the maintenance. So outside working hours, the floor robots are getting access to the office, cleaning and repairing the space. Meanwhile, the one attached to the rails, the robots A, are working on the cladding, cleaning and maintaining from the outside the shell as well. So we have planned to have the main core large enough to imagine to transport a panel through it without problems, which is 5.7 meters. So in case there is a panel that is damaged, a new one can be easily transported by robots through it. So we had to imagine all of these machines connected to the same network, sharing somehow the same brain, exchanging real-time data and warning in case of any problem. So as a conclusion, this whole exercise wants to open a discussion to embrace the change and control and design it in the way we want it to be. So we wanted to give an opportunity to think, even to argue on what we proposed as an example. So the point is start to think how we want this challenge to happen and with a perspective toward the future. So we hope you enjoyed this presentation, you feel inspired after this. Thank you.
Hello everybody and welcome to the live Q&A portion of today's show. I'd like to first thank Molly, Elif, Alina, and Fernando for taking time out to first produce their talks for us and then make time available to be here live to answer your questions and some from me as well. It's been a kind of a weird year, and so here we are all at home, and we've had a very varied mix of talks today. The first set of talks are always to try and expand the mind and to think outside the box and to think beyond the realms of the limitations that we have today. So it's really great to have 3 talks looking at robotics, looking at new workflows, new technologies, and how they can be used possibly to change the way we work today. And the thing that strikes me out of all of the talks is that every single technology that we've seen today is pretty much something which is already doable. The only difference is really the will to do it or the idea that we should be doing it. So digital construction and digital fabrication is something which we're on the cusp of it, but the people who are really pushing the kind of the technology at the moment is still in research and development. So what I'm going to do is I'm going to mix up the questions. We've had some come in. I've got some of my own. And I'm just going to start with Molly first. I mean, the thing that really struck me was the community aspect of how you've worked with communities to empower them to be part of a design process. And so how have these people reacted who've probably had no training in design, no real understanding of structures? What kind of level of engagement do you find when you go in and start talking to them?
I think, well, so
one of our most recent projects we partnered with a community organization called No West Media Center. And this was a really strategic move because they had a relationship within the community that we were working in already. So there was a trust there that was really key to the project, I think, because that No West Media Center has been in the community for 20 odd years. Some people have grown up with No West Media Center being part of their almost daily lives. And so that partnership ended up enabling us to build trust quickly within the project. But when we started this particular project, there was a lot of skepticism around if people were going to actually be able to learn new things. Actually, there was a lot of skepticism that they held for themselves around what was actually possible in terms of their skill sets and their let's call it leveling up. And we had to be very open-minded about what that would mean for how the project might transform and how it might change and how it might have to question itself even within the process of collaborating with them. But what we've seen by being open-minded and by taking people very gently on a journey with us and establishing that trust with our partnership is that we really opened up opportunities that we didn't think we would necessarily be able to get out of working in this project, not just for ourselves, but also for the people that we were working with. So we've created new jobs for some of them that will hopefully, sustain them for the rest of their lives. And it's something that I think you can only do when you have that kind of trust built in. So I think for us, the strategic partnerships with community-led organizations is extremely important. And that's a kind of something that I think we oftentimes don't do in the industry, is that we look to the processes that exist for community consultation already. Mm-hmm. And we don't necessarily think outside the box about new ways of creating, new ways of doing community consultation, which is actually much more embedded within the community itself.
Yeah, you were saying that you have internships or you have scholarships where people come and actually work with you on projects. What have any of those? I mean, I'm guessing this is fairly new, but have any of them gone off to do anything totally different? Has it been kind of like a career, 90-degree bend to go off and do something else?
Well, we had someone working with us recently who was a swimming instructor on furlough, and now she's going to be heading up a crew of builders building one of the first weekend make homes in South Bristol. Wow. So yeah, we had a woman who was her first day on the job with us, which we pay everyone a going living wage for a laborer in Bristol, which is in between 100 and 200 pounds a day. Depending on their experience level, really, and we have a kind of ratio within that. She was her first day at work after 6 years after having her son, and she was an interior architect beforehand. And it gave her the confidence to actually register in new courses so that she can increase her skills. Wow. Those kinds of stories, those are just two very quick stories, right? Off the top of my head. So yeah, there is, and that's with community members. We've also been doing work placements with 16 to 18-year-olds, and that has been very interesting. I think that it has given them a taste of what's possible more than anything else. But they're 16 to 8-year-olds, so they're oftentimes just experimenting with different options that are out there and trying to see what hat fits.
So the system you've created is very interesting. I think I might have, when I met you the first time, we were talking about Facet Homes. And Bruce Bell, who's talking on Monday, where he ships a shipping container to site, and he uses a milling machine, and he creates architecture from making wooden boxes. You've gone for a very similar, even more pared down way of producing box sections. I've got someone, Osama Hashim was asking, could this actually be used in earthquake zones? Could this be used anywhere in the world? What kind of structural strength do your box sections have?
They're very much under development in terms of structural strength. I'm not going to be able to say exactly what right now, but everything. So the more blocks, the stronger it gets. Let's put it like that. Okay. So actually, size is of interest, or number of blocks is beneficial.
And how much do they cost? Have you got a standard size, fixed price idea?
Again, we're in the process of working that out.
Okay. So I'm going to just go over to Ilif for a minute. So,
Yes.
I mean, seeing all this incredible sheet metal folding. Last year we had Tal Friedman come over and he was doing facade designs with sheet metal folding. I mean, it's innovative and fantastic, but the problem is scale. You know, at what point are we going to get really large presses to produce big folded structures from metal?
Well, I guess once we have the right machinery, Martin. I mean, there are, you know, obviously there are always fabrication limitations we are working with. And, you know, in our case, you know, at the AA, we have a really nice robotic cell setup, but, you know, obviously there are limits to the sizes of sheet metals that you can get inside the cell. So that was actually, it's a really nice question because that was one of the fabrication constraints that we had. So we were limited to 800 mil by 800 mil flat sheets. I do think that obviously as the let's say robotic cell configuration as it starts to become larger, we can scale up certain aspects of these things. I'm not suggesting that we can scale up, you know, infinitely, obviously, because there are also limitations of the material, right? And in our case, we wanted to really generate something that is lightweight. And that's also the reason why we use a really kind of thin sheet of zinc. So I think that, you know, how much you can scale up the size, these are all interrelated with each other. And it also depends on, like I say, the fabrication constraints, the material constraints. Yeah, but of course, you know, for the next round of experimentation, what we are looking into is, you know, if we could think of, let's say, a building facade element. This is also one of the things that we are considering at the moment.
Wow, interesting. I know some people who I can put you in touch with there. It was interesting when you'd also sort of put the structure together and then did the laser scan, the photogrammetry, and then you compared the model to the actual. So you did a lot of finite element analysis, and you did a lot of analysis of the structure. So how did the computer modeling of the structure compare to the actual structure? How accurate can we expect our tools to be in predicting outcomes of fabrication?
Right. Okay. So in our case, so we did the laser scanning photogrammetry for the first prototype we developed, as you mentioned, and that was really helpful for us. Okay, so I will answer your question in let's say two parts. The first part is the laser scanning was really helpful because it really showed us, for example, where the deflections were in the structure. And it helped us question why these deflections happened. Because if we come to the second part of the question, the computational model was highly accurate. It was actually too accurate. It was perfect. What the challenge lies in actually assembling the model, because it deals with manual labor, right? So you have 10 people lifting things up, and like I said, these sheets are quite thin, which means that they are really flexible. And all of the finite element analyses we did for the first prototype was actually on the completed project. So what we did for the second prototype, and this is what Berhappold helped us with, basically we analyzed it in stages according to how we would assemble it. So that actually gave us a really good idea about how to assemble the structure in the first place.
Right.
So I think that, finite element analysis, and this is what we always, talk about in Emtech, these kinds of analyses should not come afterwards, but they should really be part of the actual, design stage. And so for the second prototype, it was really helpful.
It's interesting that you're working with lightweight materials that are so easily damaged or deflected or dented, and it's amazing you can get this accuracy with a computer, but then human hands mess it up.
Yes. Yes, because exactly, because how the structure becomes stiff is actually when you connect all of the components. In our case, before you connect them, they are not stiff at all. So what gives it stiffness is the actual connection. So that's why it's really useful to conduct these analyses in steps rather than for the final outcome.
Another thing that struck me in your talk was your relationship and interaction with companies coming to you to do research. And so obviously you're trialing, I mean, you went through 3 or 4 different types of technologies that you're pushing. How does anybody who's listening, how does somebody engage with you and the AA to do the next kind of phase of research of things? Is it a case of, it's a funding issue and they come to you with funding, or you go for joint funding? Can you help them get funding for their research? What kind of things can companies come to the AA and do research with you?
I mean, there are multiple ways of doing this, basically. So like you said, we were approached by companies in all of the cases that I discussed. And in some cases, we got funding from the companies, let's say, for all of the materials that we use. And in the case of Fibrobeton, they brought in the technology itself. So in that respect, they funded us, and our contribution obviously was to develop these custom computational tools. But again, this is one way of approaching the issue. Basically, I mean, I'm not suggesting that this is the only way, but this is one of the ways. I think this is like an open conversation really between, that would take place between the AA and the interested company. But of course, what brings us really together is the research aspect. So when there are, when there's an educational institution like us and a company who are interested in research to do something together, then we can always find ways of basically collaborating and publishing our research. So
I'm just thinking if you've got a PhD researcher who's specializing in, let's say, generative design, you wouldn't reject research development interest because that person wasn't you didn't have anybody who was interested in that vertical area, or is it a case where you seem to span all of them? It doesn't really matter.
No, I mean, we don't, as long as it's an interesting research topic that deals with, technology in some sense and material fabrication, robotics, we are more than happy to collaborate. We don't, pick, we don't say, oh, this is the right topic or this is the wrong topic, because we believe there's always something interesting to explore. And, why not? We wouldn't be, picky in that sense.
I'm just going to move on to Fernando and Elena. So I'd like to thank them. I think they're together, maybe on the same video call. We met at our venue, and we gave all our talks to the empty room, which was kind of unreal. So yeah, this is kind of like a very big question, but so everything we saw architecture, we saw digital arts and crafts, we saw digital fabrication, we saw the concept of humans living with robots and the coexisting in a building. I mean, there's so much stuff here that this really is future gazing, because I never even thought about the idea of living with a robot and what that would do. Maybe the one that does the vacuuming is probably about my limit. So how do you see all of this technology affecting the role of the architect? Because here you're talking about digital fabrication, you're talking about sociology and living and coexisting. I guess in some ways you look at Gaudi's work, and he was a craftsman and he was a fabricator. In this respect, you're having to think about everything. You're thinking a lot more about digital fabrication than I would normally think of as an architectural role. So how did you come up with this?
Yeah. I remember I saw a news that explained the loss that will be the jobs that will be lost once the robots will be developed. And unfortunately, this is something that sooner or later will happen. But more than losing jobs, I think they will change. And they will need to adapt to the new realities. In terms of the architects, I don't think the architect will never be replaced by robots, but I think we need to adapt ourselves to the new reality of construction, mainly, and to try to understand how those robots build to be able to communicate with them.
I think is going to be basically something that is happening right now, but in a different way. What does it mean? It means that now we design, but we design conscious of which is construction detail, and also having a continuous conversation with the constructor. Most likely in the future, especially seeing also the other presentation, I do think that the robots will gain terrain, and we have to learn how to speak the language in a way to be able to control this change. So we will be the designer, we will be the mind behind and the brain behind that. But to be the brain, we have to understand how to speak the same language, how to develop the same kind of design, and to also find new ways of implementing it following this.
Also, the times change, also the spaces change, and the design will be different. In this case, the exercise, right, was how to change the design, the space, allowing this possibility.
Yeah. One of the questions that's been asked is, why did digital designers look for complexity in their designs? I know I could probably answer that myself, but I'll let you have a crack.
Well, I won't say make it more complex, but as soon as you have you allow you have the possibility of the freedom, right? More than the complexity.
Yeah, I see why the question is there. It looks like a very complex building, and actually it is. And but it was more. I wouldn't look at it as a shape. I would look at it as an opportunity to investigate the relation between human robots and how it will happen, and how will our role develop following that.
Actually, in the shape, it's just a crazy Sahabi style free shape.
Well,
but
it is a genius.
No, of course, this is a genius. But it's respond to what we want to achieve also structurally in the inside. So the shape of a meaning and a reason.
The funny thing is, you kind of look at digitally designed buildings. There were digitally designed buildings in the 80s, and they ended up looking like Legoland. And then there were digitally designed buildings using Grasshopper, and they can look like Zaha work and beautiful flowing curves and stuff. It's one of those things where if you've got a tool that can take the complexity out of your hands, you're much more free to accept risk and to do something which is will stand up because hopefully the computer says so in a correct way. But it was definitely a question that tickled me when I saw it. So when you're talking about adaptation, I just thought, what kind of skills, if you were training now to be an architect once more, to start again, what kind of skills do you think architects need to get to survive the next 10 years, the next 15 years, as we move towards a more digitized design and fabrication process?
Is this for us or for everyone?
This is for you. I will be asking everyone, but this is for you to start with.
Absolutely. I think the overpopulation that we have to deal with will also for have more sustainable buildings. I think we will have to deal with big scale buildings more with time. That's my opinion.
We are two independent humans, and I have a different opinion. I think we will deal with many skills. I mean, I don't think that architect has to forget about the small scale, but has to have present the big scale as well. So the human scale is very important. For example, in the presentation previous 2 hours, I saw a very human scale approach, which I like it very much because it really goes into the detail. Our exercise was different. It's more a big scale mind, but it's our role, I guess. It always has been our role as architects, seeing a small scale and big scale. From the spoon to the city, you know? Somebody said.
Yeah. So Molly, the same question to you.
Yeah, I mean, I think that working with people is a really important skill. And I think one of the things that, working with real people, that live and breathe in the kinds of places in which we're working. And I think there's a huge striation away from being able to communicate what we do to somebody who might live in a building that we might design. And I'm not talking like, a house for a rich client. I'm talking about if we're need to build, 300,000 homes a year. I'm talking about the people that need those homes and being able to engage with that. And that's something that oftentimes students aren't taught how to access that kind of way of communicating their work. And I think that that's something that's incredibly important. On the other hand, yeah, tech is important and digital skills are important, but if you can't communicate and you can't work with people, you're not going to really get anywhere.
Yeah, what do you think as the keen technologist here?
Okay, I think there are two, let's say, aspects, and one is like more of an, let's say, a population scale. I think that architecture students need to be aware of, what is going on in the world in terms of like real world issues such as climate change, the migration of populations, environmental change, densification. I mean, we always talk about these things, touch on these things, but I think this awareness requires a different state when it comes to formulating our building solutions, urban solutions. So I think that's kind of that's one part, and the other part that I want to emphasize is if I were an undergrad student, for example, I would have liked to build more. Like just building a brick wall, for example, or just building things, because, you can get all of these computational skills, but there shouldn't be a gap between your, let's say, computational skills and how you can realize them. And we always kind of face this challenge because, you can model something really fancy, but when it comes to its realization, you need to think about so many details, how to construct things, how to assemble things, like all of these things you have to be able to, in a way, simulate in your mind. And I think to be able to do that, you have to build more. You have to, make things with your hands, I believe.
So do you think the role of architects is going to become more of a role of engineer as well? Because they're going to need to know about how these things are made much more than they've done in the past.
I think it's good to know about engineering a little bit. I think it's quite fun. It's good to know how things work, how things stand up. I don't think we should approach it, oh, this is engineering, this is not my thing. I think these things all kind of go together. So I think it's good to have some knowledge on these things. Yeah. Okay, but of course, engineers, of course, at the same time, we all have our, let's say, specializations. I'm not suggesting that should go away entirely, but I do think that we need to have a bit more of an understanding of how things work and how things stand up. Yeah.
Going back to Molly, I had a question here saying, do you think robots and programming will take the place of humans in the future, especially in architecture? If not, what is the expected ratio between humans and robots at work?
I mean, I don't think we know the right answer to that question yet. First of all, no, I don't think that robots are going to take over the world. I think that that's sci-fi. But I do think that we don't necessarily know the right ratio. And I think the reason why we don't know that right ratio is because much of the construction automation that's being developed actually doesn't really look at anything other than the bottom line. It doesn't really think about preservation of skills, trades, knowledge, expertise that exists within, for example, the trades, or exists within those communities that are building the things that we need built or the homes that we need to be lived in. So I think that we need to actually kind of unravel the way that we actually develop those forms of construction automation to begin with, and deal much more explicitly with those communities to be able to understand that ratio.
And as you've componentized, or you've devised a new component to make multiple structures or buildings, are you going to develop templates for buildings so that people can then have a start point and then augment and change and customize, so that they don't have to start from scratch every time with, okay, here's the building block, it's these rectangles, and off you go? Or so you might have a community housing design, you might have a terrace building.
Yeah, I mean, we're developing a design application that's web-based, so that it can be accessed by anybody with any access to the internet. So it's much more accessible than any other design softwares that are really out there or that architects might use. And within that design application, there's certain rules, certain things you can and can't do that make sense for the building system. So, and within that, there's also a kind of social element of sharing things that are being built within the application. So that might include things like templates, and it might include things that you could potentially purchase and have delivered to your doorstep. So there's kind of like a yes and no attitude towards that. First of all, it's important for people to understand how the system works, so they need to be able to play with it. And second of all, there needs to be access for someone that doesn't really want to learn how to play with it, but just wants something that's affordable that they can get delivered to their doorstep. So there needs to be both of those options.
So is this the kind of thing that you'd want to work with someone like IKEA with, or some large corporate that could back you? Who could help you at this moment?
Well, we worked with Space 10, IKEA's research lab, last year on a project that was related to discrete furniture. And I think what we're most interested in now is finding the right partnerships in terms of being able to increase our social capital. So yes, while we're interested in partnering with companies, it's the right company that has the kind of same ethos, mission, and values that we have. And that sometimes is not necessarily the companies that you would think we'd be looking for industry partnership with.
Interesting. Yeah. Okay. And going back to Fernando and Elena, so do you think there's always going to be some requirement, a requirement of separation between humans and robots in buildings and in urban landscapes? We have automated driving cars now. I guess they're robots in some way, but when it becomes much more personal and it's in your face and you're sharing sidewalks and stairs, and I know in your building, for instance, you seem to have kept the robots into a different core, but they also kind of do other things around the building, maybe at night.
Yeah, exactly. So we have, at the moment, the robots during working hour, they are in the inner core. And we have somehow designed the circulation in a way not to have these two different worlds collapse. So not to have this chaotic circulation. So we have dedicated an allow path for the robots, which is the one that was in orange. And so, yeah, it's quite a complicated question, because nowadays we can see the robots are like standing in one position. We see like floor hostess in Japan working and directing you to the right department in which you have to go. And this it's quite scary as approach already. So imaging something that is moving next to you is something that I guess we will have time to get used to it, and things will surely develop. Maybe not in the way we have designed it, but it can be
well,
one.
It's from a point of view, there is there is different type of robots. We can see those robot arms machines or big elevators. They are robots. Of course, they are not human friendly, and we don't want to get involved in them. They are even dangerous, maybe. But we are seeing nowadays spots, right, from Boston Dynamics and many others that they have a human scale. I can't imagine share the space with them without feeling disgusting.
No. Like, for example, we can see that Amazon has developed the drones that would leave your parcel on the balcony, reading that surface, because it's an element that has been designed in that way. So it's all the conversation about smart cities and so on. So I think that there are human scales ones, and they will be developed more and more in the future. Now they are the first ones. I mean, for example, Spotted, we were talking, Martin, and you were telling us that it's quite noisy. And, I think in the future.
So last year when we had Spot arrive and they were setting it up and then it worked, I just heard this kind of robotic stomping because it's quite heavy and all its feet at the same time going down. I think I watched too much sci-fi. It didn't make me feel particularly comfortable. And you look at it and you think, okay, it's kind of cute in a way, but I think there's some way to go in terms of finesse, in terms of the sound and the way it integrates with you. It's great on a building site, but I wouldn't want this thing is not going to sneak up on you and do something disastrous to you. So I had one more question, which was for Elif. So I've got Kevin Quigley here asking, what's the benefit of this approach over optimized panel design made up of a single panel and a single joint design with panels made from pressed or superplastic forming?
With panels made from?
Pressed or superplastic forming. I think he wants to make them out of plastic.
Okay. Well,
so
the first benefit. Yeah, so the first
Sorry,
benefit, let's say, over a single panel and a single joint is obviously the amount of curvature that you can control, first of all, within the panel itself, and also through the joints. And so as you start to, let's say, control the curvature of the panels in combination with, let's say, the custom joint geometry, you start to have control over complex geometry. So that's the first benefit. In the second prototype that we did, where the joint actually was a single type joint, the component curvature and the size was changing. So that also enabled us to achieve, let's say, a complex configuration of elements. So, obviously, if you have a singly curved or a flat, let's say, surface that you want to aggregate panels with, yes, you can just work with, singly curved panels or flat panels, and that's fine. But our aim was to introduce this kind of, let's say, lightweight, materially efficient approach for doubly curved surfaces. So that would be the main benefit. I think the second part of the question was about thermoforming.
Yeah, he was really comparing the whole structure to using a different material.
Yeah.
As a single panel.
Yeah, it of course, this really depends, I think, on how you formulate the research agenda and what your interest is in terms of like which material system or fabrication system. So of course, you can work with a different material system and different fabrication techniques with the same goal of generating a complex assembly of geometries. So there are many, many options out there. Yeah.
And just trying to make sure I've got all the questions. think that's all the questions I've got, unless I've got them from a different one. The one thing I'm going to do is I'm going to mention this book, which is Molly's book. So I'm giving it a plug. But I did a lot of research about digital. I did a lot of research into digital fabrication, 3D printed concrete, robots and design, and it must have taken me 3 or 4 months. And then I found this book, and if I'd had it, it would have saved me weeks. So in this book, there's loads and loads of pretty much all the research that has been done in these areas is mentioned at some point in this book. And so if you want a good read about what's happening and what's being done, highly recommend this. We're going to give 5 of these away, and we're going to tell the people when I've worked out who's asked questions. Kevin Quigley, Osama Hashim, Francesco Pitano, and others. I will get in touch with you and we'll send you a copy. So I think that kind of brings us up to our half an hour. So I'd like to thank again Molly, Elif, Alina, and Fernando for taking part, all the effort they put into putting their talks together and sharing their work and research. So I think we're back again tomorrow with a whole load of different things. VR, the guys in Archeo gave their presentation in AR. Nate Miller, who's got some interesting technology. I can remember this. I've got so many things going on in my head. Who is tomorrow? Oh, and Julie Dorsey. Oh my God! So Julie's developed a 3D, 2D sketching program. I don't know. That makes no sense to me, but that's the final talk for tomorrow. So thanks for joining us today. Thanks for tuning in, and Next Build Virtual continues for the rest of the next week. Thank you very much.
Thank you very much.
Thank you.
Thank you.
Thank you, Martin.
Thank you.